Okay. Hello. Hello, everyone. Am I audible? All of you are,
Yes, sir.
all of you are here. Okay. I, okay. Sorry for the delay today. But yeah, let's start now. Okay. So I think this week 12. How many of you have gone through week 12 content? Like, have you at least seen what is it there? Yes. Okay. We are okay. That was the previous question. The next question is now: have you gone through the content? Yeah. Is it half? Okay. You can just maybe you can just thumbs up so that I can understand. Geeta said no. Satya, yes sir. Okay, no sir. No sir is for the second question. Okay, yes sir for the first. Okay. Half and okay. Nobody has done. I understand. Okay, week 11 content. Okay, so today's actually. Shall I wait for the answers? Okay, Yeshu has done. Other people. Oh, so this batch actually, okay, I think a lot of girl students are more. Huh? What is the question? Okay, the question is, have you gone through the week 12 content? At least seen the lectures. Maybe some of the lectures is fine. Okay, Abhishek is saying yes. Right. Okay. So this week, right? This week is actually about like all the summarization of classification algorithms, right? Probably. Why the discussion is more on the classification problem? Can anybody answer? Why we have so many algorithms for classification tasks rather than the regression tasks?
Because classification has a like a 0 1 loss, and that is not like convex, so that's why we made so many algorithms and so many convex surrogates for or the algorithms, while the linear regression and all that were solvable by just like matrix inverse.
Yeah, so they have the closed form solution, right? So all this linear regression problem, for example, is having the uh, closed form solution. Closed form solution, and that means you have some formula with which you can actually measure the loss, right? Or in this case we need the loss. Otherwise, closed form solution to any problem will be like you have certain formula where you can plug in the values and you will get the answer, right? And open form is like even if you plug in the values, you may not be able to solve that, that, or you will not be able to get some answers. That is the open form solution. So in the case of linear regression, if you see, uh, we have what kind of loss is there in linear regression? Squared error loss, right? Or we can say regression loss to that, correct? Right?
Yes,
Yeah. So, and this squared error loss, how does it look like? So
it's
basically it is w
parabola, so it's
transpose x
convex.
minus y. Okay, let's say w transpose, let's say w transpose xi yi square, right? This is my squared loss, squared error loss, right? Fine. This is the regression loss, and if you see this loss, yeah, it's just a parabola, and hence we can say that if this loss is kind of a function, let's say this function will be what, a convex function, right? What do you mean by convex function?
Which has a global minima, local minima is same as global
Yeah,
minima.
local minima is same as that global minima. Another thing is you will always have minimum value, right, for the convex functions, correct? uh, and yeah, and it is like a it is having the one local minima which is always be a global minima, right? Yeah, that is true. There are four more definitions to this, like epigraph of f and all will be there. You can actually study it later on. But okay, the why we are actually discussing this is because we wanted to see whatever algorithms we have seen already, right? Which are algorithms we have seen for classification? I think, and major. Okay, so we will not see about the Canaan and possible decision tree, but Canaan, why we are not worried about is because we don't learn anything, right? On the data, every time we will have to do the same steps. That is why we are not actually doing it, correct? Or we are not concerning about Canaan, classification thing. Okay, what else are there? Where important ones are which ones?
SVM, logistic
Eh,
regression,
yeah, SVM, logistic regression we have seen, right?
perceptron.
Perceptron algorithm. Okay, fine. So we are actually going to look into the first of this week 12 is what how this loss how these losses are looking like, right? And how what does that mean is how our models are actually performing on the classification task. Fine. So what is initially when we started the discussion of classification? What was that discussion? Discussion in the sense, what I'm trying to say is, uh, okay, yes, so
01 loss.
error, right? Yeah. So our error will be misclassification error, right? Or sorry, misclassification error, and that is also called as 01 loss, right? 01 loss or 01 error, right? I hope this is understandable. What does that mean? We wanted to see that how many mistakes we have done, right? While or how this model has performed is understood through number of misclassified or number of misclassifications, right? On a training data, right? So we actually see for the training data and then we see for test error. That is a different case, but at least we will see that during training how our model is performing, right? And in that case, how many classes are misclassified, that we actually are concerned about. So how does this data set looks like? First of all, data set will be the same as that of our regression task, right? It will be a pair of x1 y1, x2 y2 till, let's say, xn yn. Okay, okay, each xi will be in what dimensions?
RD
D dimensions. Okay, what about yi's?
plus minus 1.
Yeah, so either they will be positive class or negative class. We can say it as 0 1 class also, right? It depends on like which algorithms we are using, but yeah, nevertheless we are dealing with the binary class or binary classification. Okay, yeah, this is fine. Now what was our performance measure for any model, or in general for classification problems? What was it for regression? What is it? The minimum squared error loss, right?
Yes, sir.
Right, and here what we are actually so this misclassification error will be the important one. And how does we mathematically write it down? So for,
Indicator function.
yeah, indicator function. And how does it will write?
W transpose X is not equal to Y.
Yeah, or maybe let's say h of x is, suppose I'm saying that h of x is, can I say that sine of w transpose x,
Yes, sir.
right?
Yes.
We are actually caring about what is the sign of that, right? And that is if that is not equal to
Why?
YI.
yi, right? So that is what we are actually caring about. And how does this indicator function work? If this is true, so this is the argument, right? Let's say this argument is true, then okay, maybe let's just write it down. Let's say this is z, fine. H of x is equal to z. So how this indicator function will work. I don't know how.
If z is not equal to yi, then it will take one
No,
value.
no, z. Okay, yeah, correct. So if okay, indicator of z will be equal to 1 when
Hx is not equal to. If it
if
is
That
true,
is true.
if z, or if z is true, right? Let's say entire thing is z, not the, let's say this entire thing is z. Now this is true, right? If z is true, then it is equal to 1.
1
One and
What does that mean? We have misclassified, or we have correctly classified?
misclassified.
classified.
Misclassified,
Misclassified.
right? And if it is 0, otherwise, right? It is okay. This was the loss we have seen. I think this was like, and what is our goal?
Minimize the loss.
Minimize the loss, right? And that is what we always do, and minimize this loss for h or which functions.
Linear functions.
Yeah.
Linear
So
functions.
yeah, so we will see the class of functions which are linear, and we'll try to minimize the above loss, which is the uh, this one loss, right? So 0 1 loss. This is, let's say, indicator function of h of xi not equal to yi. Okay, fine, good. In other words, you said h of xi is what? W transpose xi, right? So can I say that, or sign of,
Sign of that. Sign
sign
of
of,
that.
okay. So we can I say that this is like sign of W transpose xi? And
Not equal.
once I said W transpose xi, what does that mean? This is already a linear function. We are actually caring about the linear function. So minimize over now, uh, which, over which
W
quantity should
W
W? Yes,
W
yeah, and W, in which dimensions it will be there? If x is
RD
in RD, then uh,
RD.
RD, right? Okay, because it will be like this, no? W1 x1 plus W2 x2, like that, right? So whatever uh, x x dimensions will be having, the same similar dimensions W should have. And sign of W transpose xi, if it is not equal to
Yi.
yi, summation over, I think should be some over all the training examples. That is what we are actually trying to do. So these two things are the same things, right? But yeah, we have said that this is the NP hard problem, right? Why it is NP hard?
It is not convex,
Not differentiable.
not
Not
differentiable.
convex, not differentiable, right? So in the, okay, mostly it's like it is not differentiable. So we will not be able to do it. If it is differentiable, then what techniques will be having generally?
Gradient
Subgradient.
descent.
Yeah,
Generation.
gradient descent
Subgradient.
method, will be having, or subgradient methods, or maybe in general, if that is like properly differentiable, right? Then we can find out its solution, right? And that will be a closed form solution, like we did it for linear regression,
Regression.
right? So that kind of techniques we will be having. So generally, this is very hard problem, right, to solve. Okay, but then that's why we move to some other algorithms. Which are those algorithms we have seen? I think we'll have. So today we are going to discuss majorly three. One is, I think, logistic regression. Then what else is there? Perceptron and the
SVM.
SVM, right? So we can actually think about the soft margin SVM also, or hard margin. That is fine. But yeah, generally these three, and we'll see that. Okay, how does this loss will look like if I wanted to draw this loss? So how does it will be? Uh,
For
so
W transpose X value less than
yeah,
0, it will be 1.
yeah. So if the W transpose X, if it is less than 0, it will be
1.
1.
Like a straight line y equal to 1.
Okay. Okay, but yeah, okay. How to think? How to say that, right? I think by looking at this equation, will you able to see, like, will you able to tell
No,
it? No, right?
no.
So we'll have to actually transform this function, right?
W transpose Xi Yi should be greater than 0.
Yeah. So we can actually write it down like this. Uh, so yeah, we are minimizing is W over three
RD.
dimensions. Yeah, RD. And uh, what we can say about it is, like, let's say summation of I equal to 1 to n sine of W transpose xi. So this will be as it is. So instead of saying that sine of W transpose xi, okay, we'll remove this part. What we can say is, maybe I'll just multiply this with
Y.
y, and
Xi
what we
Y.
can say is, if it is less than,
0, then it will be 1.
0.
okay, then we'll use the
Indicator of that.
indicator function, and we'll see that if it is
Mm.
less than 0, right? Okay, all right.
Yes, sir. Yes, sir.
Okay, maybe I can
Xi
write.
Y. Xi Y.
Yeah, see, like you will do that calculation, right? That is not a problem, right? Xi y is fine. Okay, you are saying here. Okay, fine. That's it. Yeah. So what do you mean by this part? Let us try to think about this. So initially our problem was indicator function, where h of xi is not equal to yi, right? And then we said that instead of that, what we are writing is, we say, or we can say that it is indicator of W transpose X into, or W transpose Xi, let's say, or Yi less than 0. Let's talk about only one right now. Suppose for one data point, how this is similar, right? Why this is similar? This similar argument.
If the signs of W transpose X and Y are different, then it will be negative.
Yeah. So generally, when we say equal to 1, so this is equal to 1. When this will be equal to 1 is when the sign of this function is not equal to, so that means we are predicting it wrongly, right? Then it will be 1. So when this will happen, let's say sine of h of x uh, is, let's say, is equal to -1, and then y equal to +1,
1.
1.
right? Then sine of h of x is equal to +1 and y equal to
-1.
-1.
-1.
So in this case, my indicator function will throw value 1,
1.
right? And sine of h of x equal to -1 and y equal to -1,
-1.
and sine of h of x equal to +1 and y equals to +1. In
+1.
this case, our indicator function will throw value
0.
as 0, right?
0.
These are the 4 cases we have to look into, right? And can I say the similar thing about this thing? So what? Okay, what is this h of x? We have said h of x is nothing but,
Sign of W transpose
okay,
X.
sorry, I think I have done something wrong, right? Okay, let's say, sorry, it should be W transpose X, huh? Either h of x equal to this thing, or, right? Basically, I wanted to say this, right? Because we are saying that h of x is sine of W transpose X, right? Right? W transpose X and transpose X, right? Okay. So when the W transpose X sign will be negative, when W transpose X is less than
0.
0, right? And if your y is +1, right? That means it will be positive, right? So if it is +1, the product of these two quantities will be what?
Negative.
Negative.
Negative. So indicator function for this will tell me what?
1.
1.
Less than.
1, right? Indicator will be 1.
Yes, sir.
Okay. This is negative. Okay. What about when the W transpose X will be positive, +1? When it is W transpose X is greater than 0, and let's say y. Okay, so this is y. Okay, y is equals to -1. In this case, the product will be
Negative.
negative. In this case, W transpose X is less than 0, because it is the sign of W transpose X is giving me -1, and the y corresponding y value is -1. In this case, the product will be
Positive.
positive. Here it is W transpose X greater than 0 and y is positive. In this case, the
Positive.
positive. So what we are saying here is, when this product, right? This is the product. this product is less than 0, and when it is getting less than 0, in
The
these two
signs are
cases,
opposites.
right? Yeah. In that case, my indicator function will write, or it will give me the value of
1,
1, right? And in this case, it will be
0.
0. And whether this is the same case for, so that's why these two statements, right? This statement and this statement, they are equivalent,
Equivalent.
right? So okay, so now here onwards, instead of using this part, what we are using is this part. Another thing is, what we are saying is h of x equals to sine of w transpose x, right? Okay, now can I uh, okay, so one more thing is, let's say w transpose x, we will say, okay, for simplification, what we can say is, this w transpose x is a function of x, right? We know that it is a function of x, and we are calling it as g of x. Fine. So this product will be written as like what? The indicator of g of x
G of
into
x, y.
y, right? And equal to 0. Okay. Now it is easier for us to, uh, okay, see, easier to represent our loss function. I'll just come to this graph. Okay. So here, basically here it is g of x into y. What does that mean? The product, right? W transpose x into y, this product. So when okay, let's say it is 0. So towards my right, towards that 0, okay, and on y-axis it will be the loss. So what will be the loss towards right side?
0.
0.
0.
0 loss, right? Why?
Because it is positive. W
Yeah,
transpose x is positive.
positive, right? Okay. And what about the negative side?
1.
Will be 1.
1, right? So when this product is negative, right? When the product is negative for this g of x into y or w transpose x into y, the loss will be higher, right? So that is 1. Okay. So here it is 1. So this is our normal loss, correct? How does this function is this is not a continuous function, right? First thing, because
Not
there is a,
differentiable, not convex.
yeah, not convex, not differentiable, and also not continuous as well, right?
Yes.
Okay. So fine. So okay. So we'll see different losses, and we'll try to uh, connect all of these losses together. So first algorithm which we have seen is, which is the very bad algorithm, which is what?
KNN.
KNN, actually, we are not learning anything, right? So the like the worst one will
Perceptron.
linear regression. Perceptron we have seen later, right? Okay, what we tried is, we tried linear regression applying over the classification problem, right? If you remember it, initially, I think the initial weeks of week 7, right? We tried it using the linear regression, right? For the classification task. And what we said there, whatever the value it will throw out, right? And what is the value there? What
If
is the
that
loss?
value is positive, then it will be classified as plus
Okay,
1, and
okay. What is the general squared error loss or regression loss? It is,
W transpose
yeah, okay,
x
okay. Let's say it is w transpose x minus
minus
y
y.
square, right?
Yes.
Correct. This is the
Yes.
general loss, and I'm saying you this as g of x, g of x minus y square, right? So loss for the regression, let's say if I apply linear regression over the classification problem, what you will do then? You'll find the w line, right? You will find g of x, which is w transpose x, and then you try to subtract the label. But when we do the linear regression problem, the label will be what? A real value, right?
Yes, sir.
Yes.
But in this case, it is not a real value, it is a
Plus
plus
one
Zero,
minus.
one,
minus
or
one. Or
plus
Yeah,
zero or
minus.
one.
yeah, right. Okay. So okay, sorry, this has to be written like this. Uh, loss over function and the data set, right? Is a function and the data set. So it will be g of x minus y square right? If I expand this term, what is the expansion?
Will it not be sine of that sine of
No,
gx,
no,
sir?
no, no, no. We don't take the sign. No, if I wanted to use linear regression, we don't take the sign, right?
Okay.
What we are saying is whatever the output it will throw, whatever the real value it will throw, I'll just, that is what we do generally, right? Uh, I hope
Yes,
that is
sir.
clear. And after that we take the sign. That is true. But once you will, or okay, I don't know if you're doing
Why
any,
you have to take as +1 and -1 only, na? Why you have to
y
take
will
as
be, yeah, y value will be, it is always be +1 and -1 in this case, right? Okay,
and W transpose X is like a linear function.
linear function, yeah. So this is what
Okay.
I have mentioned already. So g of x will, so g of x generally, whatever the decision will do, it will always be W transpose x. Fine. Okay, in this case, what is the expansion here? So a minus b whole square,
G
is,
square X
uh, yeah, g of x, basically g of x square,
plus Y square plus Y square
okay, plus y square
minus
minus 2 G of X Y
is to g of x into
Y
Why?
y. Okay, what is the value of y? Either
Y
plus 1 or minus
plus
1.
Plus one or minus. So it will
So
be one
Y
so
square
for
root.
the
square will be
square,
1
yeah. So for square, it will always be 1.
1
So the final expression will be, can I say that is g of x square
plus
plus
1.
1 minus 2 of 2 times g of x into y. Is that correct?
Yes.
Yes.
This is a loss for linear regression, right? Uh, so what, we'll just do some modification to this loss. If I write this loss as g of, let's say, x
Minus
y
one.
minus 1 whole square, okay, I'm just modifying it, whether this quantity will be the same as that of this thing, right? So can you just tell me what is, why I'm writing this g of x into y? Can you just, because,
So that we get it on the graph.
yeah, so like this, right? Because the original performance measure for the classification task will be written in this format, right? G of x into y. So we'll, because whenever you wanted to compare anything, your terms should be like the similar terms only. If they are there, then only we can compare, right? That is general rule of comparing anything. Okay. So okay, what is the expansion of this?
G square X
Okay, let's say g of x whole square
Same as above, sir.
Same.
y square
plus
uh,
1 plus 1
plus
minus
1 minus 2 times g
G
of
of X
x to y. So this y square here, whether it
will
One.
be
will be
1
plus or minus 1, it will always be
1.
1. So you can say that it is g of x whole square plus 1 minus 2 times g of x into y. So let's say if this is equation 1 and this is equation 2. So I can write this g of x y, sorry, g of x minus y to the whole square as g of x y minus 1 to the whole square, right? Okay.
Yes.
So if I wanted to draw this here, so what is it? Let's say now this is g of x y minus 1 whole square. So where it will intercept x axis or g
1
of x y axis,
1.
it will intercept at 1, right? And it will be a parabola,
Yes, sir.
right? And when g of x y uh, g of x into y equal to 0, that time it will cut at 1, right, on the
Yes,
y
sir.
axis. So can I say that this will be a parabola which will go through this, right? Fine. What is the problem with this loss now?
Even if it's correctly classified, it will throw up a large value. When g of x is big, it will throw up a large value. Even if it's on the correctly, even if it's correctly classified.
Okay, so let's say g of x y, that product, right? So the product of that value, if it is very high, uh, okay, what does that mean? Even if it is on the right side of it, then in that case the loss occurred will be higher, correct? uh,
Yes.
All of you are fine with that part, and that's why this is not a good case, right? Good case in the in the sense of we cannot actually classify it properly. So
So the problem is towards the right of one, sir.
yeah, right of one, right?
So because after to the right of one, the it is correctly classifying, but the error is high.
Error will always be high, right? So and that is not desirable thing, right? If the error is high, then generally that is not a
It
good
will
case.
keep on iterating over
Yeah,
and
yeah,
never get zero error.
right, fine. So that is the problem with linear regression, and that's why we discard that algorithm. What was the next algorithm we have seen? The good one is, I think, perceptron we have seen very later stage, right? At the end. The next one we have seen is support vector machine, right? Correct. Support vector machine. In this case, let us consider soft margin support vector machine, right? Or SVM, soft margin SVM. What was the what was the loss function, or what we tried to minimize over there? It was,
Maximum of 0,
Non W square.
0 and W
can
transpose.
you just tell me the dual, like, can I say that it was minimum of W comma epsilon half
W
W
square.
square? Okay, just give me a 2 minutes. Okay, just sorry. Okay, so yeah, where were we? Yeah, what is this? Is this known to you, right? This part,
Yes, sir. Plus C into
because we when we do maximization, actually we do one up or two upon norm of W, right? Square, norm of W square, right? If I wanted to do minimize, then we do like this, right? Square plus some
C
constant,
into
and we give some
summation
uh,
I equal to 1 to n
n
epsilon I.
epsilon I is, right? So all the, so if you wanted to get that data point, so this is to accommodate outliers, right? Correct. So this was the problem for us. I hope this is fine. And what was the constraint over that?
W transpose xi
Yeah,
plus
correct.
epsilon
W transpose xi
plus
into
epsilon is greater
yi.
than
No, into
into
yi.
y
Yi, right? No,
plus epsilon
plus epsilon I should be greater
greater
than or
greater
equal
than
to
equal to
1.
1.
And what was another constraint, which is
Epsilon
epsilon
I
I
equal
should be
greater than equal to
or equal
0.
to 0, right? So we need to give some bribe. The bribe in the sense, if you wanted that outlier to be classified correctly, we actually take that outlier towards the, let's say if it is on the positive side, we need some amount of or we give some amount of bribe to that data point, or you just add that data point some value, so that it will go to the left side, right? Or maybe on the negative class. That is the meaning of it, right? So I hope that is clear. So soft margin classifier generally does it for generally we do it for accommodation of the outliers. Okay, right. What is the next step? Okay, or not next step. What I'll say is, maybe we will reconfigure this part. Okay. Okay, what does that mean? The objective function will be the same. So the objective function is minimizing over W and X epsilon. And what is another important thing about SVM? This W will be any specific W or it can be any W. I think that is the important one. It can it be a zero vector?
No.
It can be, right?
If C is 0, then it will be 0.
So no. So what I'm saying is, when I have that hard margin classifier or hard margin SVM, that W cannot be 0, right? Because we say that we have that margin, if you remember it properly. So we will add that margin if I'm not wrong, right? So
Yes,
that
sir.
W cannot be a zero vector in that case. But in the case of short margin SVM, we allow all the W's, right? Including the zero vectors. Is that a correct statement?
Yes, sir.
Is there one doubt?
Yeah, tell me.
In hard margin, within the margin, there should not be any data points, no?
Yeah, that is what. So, okay, how does that will look like? Let us say you have this thing, right? And we see, if you remember it properly, initially when we started the discussion of SVM, I think we discussed about the perceptron also. What is the perceptron issue? It was happening. So if that was going through this, right? So let's say you have some plus or minus, right? Without the margin, what will happen? You will get like will end up into not classifying it correctly, or it will not converge, right,
Yeah.
at certain point of time. And that's why we have introduced one more term, that is
Margin.
what? The margin, right? So we said that there is a margin. Okay, this is not a proper diagram, but yeah, just understand. And we said that any data points which are over here, so say, right, they are called as a support vectors,
Yeah.
right?
Yeah.
And there will be some margin here, right?
Yeah.
So this is the W line, right, or
Mm.
W vector,
Okay.
correct?
Yeah.
The line, what is the equation of this line? W transpose X equal
Equal to
to
0.
0,
Yeah.
and this x's will always be, we don't need all the data points, we need only those vectors which are on this lines,
Okay.
correct na?
Mm.
and and this is, let's say, and what is the equation of this line? W
W
transpose X is
equal
greater
to
than,
Will be
1.
equal to
1.
1.
okay, okay,
Equal to 1.
1, let's say 1 in this case, okay. And what about this?
W
Less
transpose
than
X
or
equal
equal
to
to 1,
Less than or equal to, sorry,
minus uh,
right,
minus 1,
1. 1.
minus 1, or what is it?
minus 1, minus 1.
Minus 1.
Yeah.
Y
Or
is negative.
I think it was equal to 1 and equal to minus 1. I think that is the thing,
Yeah.
right? That is what we said. But in this case, if you think about it, if I can I is it possible for me to get a zero vector as for a W?
No.
No.
Because if I get it, then what will happen? Will this hold? This will
No.
not hold, right? I hope it is fine. It is
Right.
understandable.
Yes.
Because why this is there? Because we are actually keeping it some margin, right? No, we are saying that there should be some gamma, right?
Yeah.
And because of that, that W will not be, it cannot be a zero vector. But when we say about the soft margin SVM, in that case, this W we can allow for 0. Why?
Some
Because we
penalty.
are actually providing the bribe, right?
Yeah, right.
So
Yeah.
if this is if it is 0, it doesn't matter, right? Because if you have some value along with C, actually it can minimize that part. I hope that's okay. If my C is equal to 0, in that case what will happen?
W will be equal to 0. Alpha is equal to 0. And if alpha is equal to 0,
W will be 0. And if C equal to infinity,
then it will be a hard
Hard
margin.
margin.
hard margin, and that means, will that be a zero vector? No, right now no,
No.
right?
No.
Then that is not possible, right?
Yeah.
I hope that is fine.
Yes, sir. Yes.
Okay, so that's okay. Maybe you can just revisit it again. This was not support vector machine is little bit a difficult concept, but okay, that is not a problem here. Okay, but I hope this objective function and the constraint. So this is a constraint optimization problem. Here, this is my objective function, and these are the constraint. So okay, again we need to compare the losses here. So can I restructure this part. So let's say this was my part. Okay, maybe I'll just add one more page here. Okay, just think about the constraints here. What are these constraints? Can I write this epsilon I from this? Let's say this is equation 1. Can I write it as epsilon I is greater than 1 minus W transpose xi into yi?
XIY.
Can I write it like
Yes.
this? Right, I'm not doing anything here. So let's say this is such that. And what is the another constant? Summation of sorry, epsilon I
Can be
is
more
greater than
than 0.
0. So if I look at this two constraint, what can I say about epsilon I from this? So either it can be equal greater than equal to 0, or it can be greater than equal to this point. When this will become equal to 0? When this part will become equal to 0?
When W transpose xi yi equal to
Equal
1.
to equal to 1, right? And can it go to the negative side?
Yes.
It is, right, it is possible. But if that goes to the, okay, if this quantity goes to the negative side, will this be allowed? Not allowed,
Not allowed
No.
because of
constraint
this
is
constraint,
set.
the second constraint, right? What I'm saying that this epsilon I will always be, either it will be equal to 0, or it will be a positive quantity, right? So this case is not allowed, right? Correct. So when this 1 minus this thing is negative, it is not allowed anytime. I hope this is understandable. So can I write this two into one form by saying that epsilon I can either be the maximum value between 0 and 1 minus,
1 minus W transpose XIY.
uh, can that satisfy these two conditions?
Yes.
So when this will be 0, when this quantity become
Negative.
negative,
Negative.
and if it is positive quantity, then in that case it will write down
Return
the
that
positive.
positive.
I hope this is fine. These two constraints actually I have written into one. This is okay? Any doubts
Yes,
over here?
yes, sir.
No doubts, right? Okay. And what we have said earlier, that this is what?
G of
G of
x.
x or G of xi. Fine? Okay. Okay. Now we do more modification, and what we can say that what is our objective function here? Minimizing over w and epsilon, half norm of w
W
square
square
plus
plus
c
C
times
into summation
summation
of one I
I
going from
equal to
1
e.
to n.
Now
Max of
epsilon, right? Yeah. So now I
max
can
of
write max of
0
0 comma 1
1
minus.
minus W transpose xi y.
This is the same problem as that of written over here. I hope this is okay. Okay. Uh, Another thing we have seen in the lectures previously, in the case of ridge regression, and okay, what was the ridge regression? Uh, okay, or how we have done that? We have added some regularizer, right?
Regularizer.
And what is the use of regularizer there? To suppress the weights, right? Or to get, or anyway, like maybe the ridge regression, or in the case of lasso, what we do is we added some regularization parameter, and that parameter used to uh, for certain data points, it will give me closer to zero values or zero values in case of uh, lasso, right? So we'll remove some redundant data points, fine, or sorry, not data points, features. In this case, let us consider this w as a regularizer, riser, and okay, so, and this is okay. One more thing is how is dependent on, right? So this is dependent on data. Do you think this depends on data?
Yes, sir.
Why?
Yes.
W
XI, Y.
transpose, it depends on W transpose.
Actually, it depends on
X I
xi
Y.
and yi,
Y.
right? Here, if you see, it is only w. We are not concerned about what is the data point there. Think about this as a regularization parameter, and this basically depends on the model, right? Model dependent. Which model we are actually using, it is dependent on that, right? uh, so basically this is the dependent on the model. So this thing is dependent on data, so it will contribute to our loss, right? Okay.
Yes, sir.
Okay.
Sir, one question here. Why is epsilon the max of, it is greater than either of these, right? It is greater than either of 0 and 1 minus W transpose Xi by I.
Yeah, that is max of, right?
So, no, it can be even greater than both of these, right? Suppose 1 minus W transpose Xi by I is negative.
Okay, then in that case it will
Then,
say 0.
but why it should be 0? It can be greater than 0 also, no? Because that will
This
also
case, this case,
satisfy.
this case. No, no, no. See, this is the first constraint, right? So let's say this quantity is negative, okay, or okay, entire quantity is negative, right? uh, that definitely means this constraint is not satisfied, right? If this is negative, this constraint is not satisfied. Fine.
Yes, sir.
Why it is not satisfied? Because of this. So what we have to do? We'll have. Will you take like some other value, or will you take the which is the nearest one? Zero, right? You'll take
Yes,
zero. You will
yes,
not go
sir.
for like one or two. Why? There is no support to that, right? See, if already my quantity is negative, what should I do to make it correct? I'll just take
Take it
zero
up to
value.
0. Okay.
Zero, right? I will not go above, right?
Beyond that, okay.
Yeah, it is not required there. So that's why we just say that it is zero. If it is positive, then in that case, yeah, that is it is actually, if this quantity is positive, then it is actually satisfying both the constraints, this one and this one.
Yes, sir.
That is why we are
Yeah,
written as.
yeah, it is also an indication of error, no? So we want to keep it at minimum.
Yes, basically it is not an error, yeah, but the thing is, it is yeah, it is like kind of a
Bribe.
bribe, right? So that means you wanted to make that data point, which is an outlier. Let's say it is in the positive class. You wanted to make, since it should be in a negative class, what you are saying is you just add that quantity into a negative class. But okay, we just add it, we'll have to move that to that part, that it just get classified as negative, right?
So
Beyond that also it
minimum
will become
minimum
negative.
quantity you
Yes,
have to add to
yes,
it.
yeah, yeah. I hope this is now, this is fine. Visually it
Yes,
is clear. Okay. Okay, so this is the loss, right, which actually will be occurred, correct? Is that correct?
yes, sir.
Okay, but how does this loss will look like? Now can I say that, okay, for one data point, can I say that it is max between 0 and 1 minus, can I say it is g of x, or okay, let's say g of x into y, correct?
Yes, sir.
Yes.
Okay, then how should I draw this loss now here? Now this is okay, this was the regression loss, or it was a squared error loss, right? Then the next one will be max of 0 and 1 minus
1 minus
g of
gxy.
xy. So g of xy, if it is more than 1, it will be,
Negate. It will be 0. It will be 0.
It will
it will be
go
It will be
turn
more
it will
than
towards
take,
the.
negative.
no, no, it will take the value 0, right?
Yes, sir.
Yes.
Because
At
we need
Because
to take,
the second term will be negative, so it will
yeah.
take 0.
So will it be the green line, this one?
Yes, sir.
yes.
Okay,
Up to
and
1. Or from starting from 1.
from 1, right? We'll have to
Yes,
start from 1. And if it is, if this quantity g of xy is less than 1, in that case,
then It will be linear. It will be 1 minus jxy.
right? And when g of xy equal to 0, then in that case the quantity will be
0.
1.
1 1. If this
Okay,
is
g of
0,
xy is 1. Okay, right.
so can I say that it is a line going through this,
Yes, sir.
Slope will be 1.
correct? Fine.
Minus 1. Slope will be minus 1.
Slope will be minus 1. So this
Yes.
this loss is actually called as a hinge loss. And why it is called hinge loss? Because it looks like a hinge right here at 1. So this is called as a hinge loss. This one, okay, I'll just write down all the things. This squared error loss or squared loss. No, squared error I can say, or squared loss I can say, right? And this is called, the green one is called hinge loss. And when we get this hinge loss in case of SVM, okay, this one is like, this is what the classification, basic classification loss, sorry,
Zero one.
classification misclassification error, or I can say it as 0 1 loss, right? So which one looks better now to represent my 0 1 loss currently?
Hinge
Hinge
loss.
Hinge.
loss. Okay, okay, fine. Okay, let us check now with the another algorithm. What was that algorithm? That was our third algorithm we have seen is logistic regression, right? uh, okay, what we used to do there, if you remember it properly, what you do in logistic regression, for every
Maximum
data point,
likelihood.
yeah, but for that every data point we consider it as a coin, right? And we
Yes.
toss that coin and we say that the probability, there are probabilities associated with positive class and a negative class, right? And whichever is the maximum probability, we say that that is your uh, that is the classification, correct?
Yes, sir.
And so if it is a Bernoulli trial, in that case what will be the likelihood of that? So we try to we try to maximize the likelihood for W. And how do we write the likelihood for Bernoulli trial? So generally it is like
Probability.
p to the power how many number of times you get, let's say,
Z. 1
correct,
minus p to the power 1 minus z.
right, like that. This is your general Bernoulli trial. In this case the probability is dependent on what?
The
Logistic function
Logistic
sigmoid
function.
function. Yeah.
or sigmoid function. And what is that function? Sigmoid function. So
1
it
by
is
1
written as
minus
sigma of, let's say, x,
w trans.
that
1
is
by
1
1
upon 1 plus
1
e to the
minus
power w transpose
minus
x.
x minus x. Sigma x is minus x, right?
If sigma x is W transpose
Sigma,
x.
if you take the argument as x, then it is to be e raised to minus x, right, sir?
Okay. Let's say, okay. So in that case, let's say I'm trying to say that z, and I'll say, let's say, e to the
Minus
power
z.
minus
Minus
z,
x.
right? And z is equal to,
W transpose
W
x.
transpose x.
fine. Okay. So let us
So
say,
here we are taking the threshold as 0.5, right, sir?
yeah, yeah, yeah. In this case, it is 0.5.
Okay.
Or okay, I'll just write down it as a here. Let's say it's an activation function, and let me write it as a, and z, I'm just saying that it is equal to, or it belongs to class. What class we will be having here? It will not be minus 1 plus 1, right?
Yes, sir.
More
Zero
than
one.
threshold, less than threshold, like that.
Yeah, but the classes will be not positive negative, it will be 0 1, right?
Yes.
Yes.
Probability.
Okay, so this is the case. So can you tell me what should be my, so let's say sigma of w transpose xi to the power zi,
Z.
Zi.
and 1 minus sigma w
W
transpose
transpose
xi
x.
1 minus
1
z.
minus z.
Okay. Uh, sigma w transpose xi to power 1 minus zi. Okay, I think this is your Bernoulli uh, likelihood, and you wanted to maximize it over it, right? But now when we are actually comparing the terms, right here, comparing the losses, uh, here we are not actually dealing with 0 1 classes. We are dealing with the -1 and +1 -1 class. So can I say that zi equal to 1 if y equal to
1.
+1 positive class, and zi equal to -1,
0.
Z
sorry,
equal to
1 with
0,
0, yeah, 0 when
y equal to -1.
if yi equal to -1, right? So I'm just saying that for positive class, we are actually here in logistic regression, we say that it is a it is +1, and for the negative class we say it is equal to 0. So yeah, so next term will be what? Here we take the log, right?
Yes, sir.
And the log likelihood will be,
Zi
so it will
summation
become
I going
summation
from
now. Yeah, summation 1 from 1 to n,
Zi
zi into
log
log
of
of
sigma
sigma
W
w
transpose
transpose
X
xi, uh,
plus 1
here
minus
plus
Zi 1
1
minus
minus
Zi
zi, uh, log of
log of 1
log
minus
of 1
1
minus
minus
sigma
sigma.
del transpose xi. Okay, I hope this is, until this part is clear. We are not doing anything new. It is like same thing. Okay. Now, if I wanted to convert this maximization problem into minimization problem, can I do it? Okay, can
Yes,
I?
sir.
It is possible. Why it is possible?
Change the
This
sign.
likelihood is actually is a convex function, right?
Yes.
Or currently it's concave, let's say, and we can actually, that's why we are able to do that. Otherwise, we will not be able to, right? Normal log function, only log of x function, will that be a what
Concave
is it?
function.
It's a concave function, right?
Yes, sir.
All of you agree with that? I think that graph will be like this, something like that, right? This is a log graph. It's generally it is a concave function. So
Let we
I
take negative log.
yeah. So if I no, no, I'll change this to minimization problem. So minimize over w. What it will be? Ah, yeah, that is correct. So we'll take the negative log, and what it will be then?
Minus
Minus
Zi.
a log of sigma w transpose xi. Okay, plus
Zi
1
Zi
minus,
minus
minus
1.
1.
I can do that, and then log of sigma w transpose
1
xi.
minus
Ah,
1
okay,
minus
1 minus. Okay, right. Fine. What we have said here, when z equal to 1, y equal to +1, and when z equal to 0, y equals to -1. Now let us think about this part. Uh, what will happen if y equal to +1? Okay. uh, what I'm trying to say is, let's say when z equals to, so we'll see two things, which is, let's say zi equal to 1.
and y equal to 1.
So z equal to 1 means y equal to +1, right? So we'll have to see what kind of loss we are going to occur, or incur about this, and that will be equal to what will happen to this term.
Second term will
So
vanish.
this will become 0, the second term, when z equals
Yes.
to 1, right? In that case, will have to deal with only
First term.
first term. And how does it will look like? So z equals to 1, and in that
Minus
case it
of
will
log.
become minus of log of sigma
Sigma W transpose xi.
xi. And can I say, can I write it like yi here?
Yes, sir.
Yes.
Because y equal to 1. Yes.
So it will be y equals to 1, right? uh, and this is true only when y equal to 1, because then that case zi equals to 1, right?
1.
So this can be written as minus of log of sigmoid function. How can I write now for this?
1 minus 1 plus e to the power w transpose xi yi.
Say
Yi.
by, right? We're taking the log of this part. So if this minus sign goes into this log, it will become
Reciprocal.
Log
log
of
of
1 plus
e to the
E
power.
minus W transpose XI Y.
Is that fine?
gx gxyi
Yes.
Yeah. So we already said that W transpose xi is nothing but
gx
g of xi. So it will be 1 plus e to the power minus g of
gxy.
xi into yi. Okay. This is my first thing, or first, let's say, loss for when z equals to plus 1.
1 and y equal to 1.
Yeah. So, and what is the next class in the logistic regression, which is a zero class, and that will happen if y
Y
Y
equals
equal to
is
minus
minus
to
1.
minus 1. Okay, this is second thing. And okay, let's try to understand that part. So when zi equals to 0, so the first term, this term will become
the 0
0 and will be remaining with the next term. And how does it look like? z,
minus
z
1
equal to 0,
Minus log
so minus of log, right? So it will look like minus of log of 1 minus
1 plus
sigma of
W
W
transpose
transpose
XI.
xi. Now I'll again write it as let's say yi here. Can I write it down yi? Okay, let us say maybe I'll write it down later, because of that minus sign it will change a lot of things, right? It will become positive actually. Okay, okay, we'll do that maybe after some time. Uh, next thing is minus of log of 1 minus what is sigmoid of this 1 upon
1 minus 1 plus e to the power minus w transpose x.
xi. Okay, okay, fine. If I multiply this to this, so what is the multiplication or simplification of this? So this term will be multiplied with this. So in the numerator, it will become 1 plus 1 minus
Mhm.
W transpose xi minus
Minus
1
1
divided by. So what
1
I'm
plus
doing here is I'm just making it the common denominator. So transpose xi. Fine.
1 will cancel out.
So this one and this one will get cancelled out. We will be remaining with minus of log of e to the power minus W transpose xi divided by 1 plus e to the power minus W transpose xi. Is that okay?
Yes, sir.
Okay. What else we can change here?
Take negative to inside the log.
Okay. So if I take the negative inside this log, what will happen? Log of 1 plus e to the power minus W transpose xi divided by e to the
E to
power
the
minus
power
W transpose xi. Okay. Uh, okay. What we can just this, if I wanted to remove this part, how does it will look like now? Uh, can I
We
say
e to
can
the
that
write
power w
as
transpose
log
xi
of
plus
1
e
1.
to
upon
the power
e to the power like this
Plus
plus
1.
1
plus
1
1, right? So this will become, so this part actually e to the power
E to
minus
power
W transpose,
W transpose XI.
this will
e to
become
the
plus,
W transpose XI.
right? Plus, it will become plus.
Now we can
After,
add that Y.
so next thing is, so I'll write it like normal our terms. It will e to the power W transpose xi. Now if I wanted to add yi here, will
add the
that be,
negative also. Oh, you have to add a negative also.
why we needed negative here?
Yi is
Y is
negative.
minus 1.
So I need to make, because this quantity is positive, right? This quantity over is positive. So if a yi is minus 1, I'll have to somehow make it is this entire quantity to be a
Positive.
positive one. That's why we are actually adding minus 1 here. Okay, I hope this is clear. So let us see. We have seen this part, 1 plus e to the power minus g of xi into yi. And what is this part now? Okay, if I wanted to write in that
Same thing.
terms, it will be log of 1 plus e to the power minus g of xi yi. So this loss is same for whether it is a positive class or negative class, right?
Yes, sir.
And okay, and what is basically we wanted to do it here is minimization, right? Minimize. So okay, maybe I'll write it down. So the final thing will be minimize over the w log of 1 plus e to the power minus g of xi yi. That is what now the goal. Is that fine?
Minimize over W summation of that.
Yeah, summation of logs. Fine. Okay.
And for
And
individual, it will be the log. Individual, it will be log 1 plus e
yeah,
to the power
so
minus.
if I wanted to now draw into this part, it will be what now? Third thing will be logistic loss, which will be
Log of
sorry, log of
1
1
plus
plus e to the
e to
power
the power
minus
minus gx. Yeah.
y. Okay. So when this product will be positive and when this product will be negative, uh, but anyway, it's a function of uh, or it's a logarithmic function, right? Anyway.
When gxi is 0, it
Mhm.
will be log of 2.
Log of 1, which is 0,
Log of
right?
2. Log of 2.
Okay. So
Gxi,
yeah, okay, that will be, yeah, log of 2. So it will be some quantity, but it will be
yes.
less. Log of 2, I think it is lesser than 1, right? Less
Yes,
than
sir.
1.
Yes, sir. Log of 2.
Okay. So I think this will be looking like this. Will this quantity become 0 log of anything?
No, can never become 0.
So it will be asymptotic, right? As my, so if this becomes positive, this quantity becomes positive, e to the power something, it is always be some quantity. Okay, I think I have done badly.
It will be close to 0, but never 0. Yes.
Yeah. So as it is going to increase, right? Because it is already 1 plus something, right?
Yes, sir.
This quantity is 1 plus something. Even this part, if it will, like, as g of xi into yi, that product becomes large and large, this quantity is
It,
going to get lesser and lesser, but still it is 1 plus some quantity, right? So it will try to get it 0, but it will never get to be 0, but
0.
that's fine. So this also performs better, right? Like, at least better than the squared loss. Maybe we can say it's comparable to your hinge loss, and this loss is what we can call this loss as the,
Logistic loss.
yeah, logistic loss. Okay, so these three are there.
So
Uh,
difference between the hinge and this loss is that this is differentiable at all points, right?
uh,
This
this is a continuous function, right? Anyway, because
both are continuous, but
That
this
is
one is
piecewise
differentiable,
continuous.
piecewise. So hinge loss is a piecewise continuous, right? Because you have
and it
once,
is not differentiable at
The one
equal
point.
to 1.
yes,
Yeah.
right? So that's why it is piecewise, no? So one side is differentiable, and so, right. But I think uh, oh yeah, logarithmic is a smooth function anyway. So logistic regression, so when to use this, like, okay, when you are going to use all of this depends on, like, whatever, how is your data point or data sets, right? And whichever is giving you the, because these losses are dependent on what, mostly they are data dependent, right? That is clear, right?
Yes, sir. XI, yes.
So every time, so whatever your data is there, uh, it is already dependent on that part. Fine. Okay, so I think there is another case for perceptron. Let us try to look at, so perceptron will be the similar as that of hinge loss, or will that be a different quantity?
Like hinge loss.
Huh? Okay, okay, we'll look at perceptron algorithm. What is the update rule in perceptron algorithm?
WT plus 1 equal to WT.
Perceptron. In the perceptron case, it's like the very simple one is, when you do the
W.
mistake, in that case,
If
you
you
will,
don't do the mistake, then you don't do anything. If you make a
yeah,
mistake, then you add.
XIY.
yeah.
Yeah,
Absolutely.
So
XTYT.
whatever the data point we do the mistake, uh,
We add that
we add
into
that,
the label.
right? So in this case, uh, So when we say about hinge loss, so hinge loss we defined for SVM. SVM and perceptron are actually nearly very same, right? So possibility is that this losses might be the same, but yeah, okay. We'll have to see, right? What is the loss there? Uh, so let us say what is the loss. So when you have W transpose X into Y, right? If that quantity is less than zero,
Negative. Okay,
in that
then
case,
you
what
do
is
the
the
you do the addition. You do the
what do you add?
addition. XTYT.
Okay. Can I say that XY? Let's say we'll talk about one point now. Is that fine? Why I'm saying is, let's say it is a gradient, right? Kind of a gradient. So your gradient descent method, what do you do generally in the gradient descent method? It
We
will you
minus
take the
of
yeah,
eta
yeah, right. So
and that
this,
whatever differentiable function we have.
so is this the correct thing? If I have less than zero, and that means if some mistake happened, what do you do here?
You said it's correct if we take eta is equal to 1.
Okay, and what about W transpose X into Y greater than zero?
Then you don't do anything.
0
You don't do anything in that case. What does that mean?
Zero. Yes.
Zero. So two we have seen. What is the third case?
equal to
Equal
0,
to zero.
non-differentiable.
Equal to zero. This you got the idea, right? Y minus XY. That is the penalty we are actually doing, right, into the W. We are adding that penalty to that. This is called actually delta L hinge. Hinge. It is kind of a hinge loss. Okay, but that is fine. What will happen when W transpose X equal to into Y equal to zero?
It is similar to you don't do anything, right?
So
You
that means
don't do anything.
you have a choice to select or yeah. So can I say that either you can select for a or either you can give that this thing, or you can do that is the case, right? It is not clearly defined. So in that case, can I say that it is minus or zero, any value between this into xy in this
Subgradient.
interval? Yeah, that is subgradient method. But why we are doing it? So I have, so what maximum quantity we can do, or what change we can do? Either you can do zero. If you do zero, that means what? You are actually classifying it as correctly, right? Or you can say that it is not classified correctly. I'll do the penalty of minus xy. Correct, right?
So how come
Yes.
minus XY came, sir?
So okay, let us say when you do this part, okay, in the case of perceptron, what we do generally, uh, we have okay. Do you agree first of all why we do this? Huh? Let us say your
It is
weight
clear that it is a hinge. It is clear that it's a hinge.
hinge
But
loss, right?
why
Okay,
it
so
is?
hinge loss, how it look like? Okay, let's say that is this part, right?
Yes, sir.
Correct.
If it
So
is
when
less
you
than zero, then it will be less than zero. Then it will be zero.
yeah, okay,
It will
so
be
okay, hinge at, but it will not hinge at one actually. It will be hinge at
yes, yes,
it's
zero, zero. It will hinge
at
at zero. Yes.
zero, right? Because that is not the same as that of that as that of SVM. So here, when it is negative, right? What you do? We'll have to add that penalty, right? Which is
The
equal to
loss will be
minus
there.
xy.
Yes.
If it
But
is
why minus
greater
X?
than, yeah, we'll see. So let us say if it is greater than zero, in that case we don't do anything. But what about at the point when W transpose X into Y, which is, let's say, g of X into Y, that is equal to zero? So either, see, this is the point where the distinction happened, right? I can choose either this side or I can choose this side, right? Do
Yes.
you have any correct sure short decision that okay, I should do uh, I should classify it as correctly, or I should not classify it as correctly?
Generally, greater than or equal to zero, we consider to be zero, right, sir? Greater
No,
than or
that
equal?
is because for simplicity we do, right? But if you think about it, this is the function. This is a hinge loss. What is this function basically? Can say it is max of 0 comma minus xy,
Yes, sir.
or not minus xy. It will be minus w transpose xy, right? Now, is this correct? This loss is correct. This is a
Max
loss
One
of
loss function.
if gxy is positive, then you take 0. If
Hmm.
Yes.
gxy is negative, okay, yes, sir, right.
Loss
Yes.
loss. If I think about the loss
So this
property.
graph is equivalent to this L.
Yeah,
This
see this
graph
loss.
is
Okay, this loss you can. Do you agree? This loss is 0 and minus w transpose xi. If I take a gradient in the sense del of L, what will be the loss when? Okay, because we this is max, right? We'll have to anyway remove that part max of, because we can't do it, right? So let's say w transpose x into y. What is the loss when it is greater than 0?
if it is
Minus
great,
x.
then it's 0. Then
minus
it's 0.
xy.
Should be 0 because minus xy, but I'll have to take max of this, right? Max between these two quantities, right? When
Yes,
this
that is
is
0.
negative, it is equal to 0. When this quantity is positive, right? In that
Then
case,
x minus xy.
minus xy, right? But when it is equal to 0, when this quantity is equal to 0, what is the gradient? There is no gradient. What does that mean? This function, this max function, is not differentiable at,
0.
right? So if it is not differentiable, then anyway we are actually will not be able to use any gradient method, right? So there is a subgradient method. I think it is not taught, but yeah, there are methods. Subgradient is, and how many subgradients we can get here at 0?
Infinite.
Infinite.
Infinite,
Infinite.
right? So these are the subgradients. We can get infinite subgradients there. So what we are saying is this subgradient. What is the slope of this subgradient? So what is the slope of this subgradient?
It will be
0.
minus xy to 0.
No,
Yes.
right? No. So are you able to appreciate this part? Okay.
The slope can be anywhere
So
between minus xy to 0.
yeah. So if I take this slope, it will be
0.
0.
0
If I take this slope, it will be
minus 1.
right. Yeah. And if I take like any other, so it will be some slope. Can we get the positive slope? The positive slope will look like this. Will
No,
that be
no,
possible? That is not
No.
no.
possible, right? Because in the gradient, what you should do at that point, it should be tangent to that point, right? Correct. It cannot
Yes.
be perpendicular to that point. That is true, right?
Yes, sir.
So the value it will take will be uh, so it will this at this part actually it will be minus 1, right? Along this blue line, this will be minus 1, right? Here it will be 0, and I think all the
Minus
lines
xy, sir. Minus xy or minus 0?
minus xy. So okay,
Minus xy.
this is minus xy, right? The gradient. What is this function? This loss function is,
W transpose
yeah,
xy.
w transpose xy.
Minus W transpose xy.
Okay, minus w transpose xy. And what is the gradient here at this point? It will be minus xy,
Yes,
right?
sir.
And what is the gradient here? 0. So
0.
all the lines which are passing in this region will be applicable for what case?
For the subgradient.
Yeah,
Yes, sir.
subgradient, or when we need subgradient, when the w transpose x into y is equal to 0.
0.
That is clarified now.
Yes, sir.
So all the possible lines which are actually, they are the possible candidates for the subgradients, right? So that means they can we can take any value between them. So basically in the perceptron case also, it will be a hinge loss, right?
Yes, sir.
That will be a hinge loss. uh, but yeah, anything can be happened, right? So again I can say that any line between this can be a possible line for that loss, correct?
The hinge will be at 0, sir.
Yeah, okay, so let's, yeah, so it should be like that. Okay. That maybe you can, yeah, should be like this and this part. Okay.
And that dotted line will be minus W transpose XY.
Yeah, that is right. No, that is because we just already said it g of x into y. We are actually plotting that g of x y over the loss,
Yes.
right? Okay.
No, but we're taking y as 0 and 1. So in 0 case, it will
Yeah, so it is not like exactly the same, but we wanted to look at
shifting
it
it.
like that. Yeah. So it's like it's not the same thing. We are trying to look at it, but this is not same thing. Anyway, we don't use perceptron in the practical cases, right? We always go for the SVM. So SVM's loss will be considered as the correct one, right? In the practical cases, because you'll definitely will have the outliers. There is one more term I think there, which is what the boosting loss. You can learn it from, like, maybe it is not covered actually, so I'm also not debating on that. Let us try to see the last part, which is what the neural networks. Why we need a neural network, or any other thing? Why? Okay. So what was our general loss definition for any regression or classification case? We try to minimize W for,
Predicted value minus the actual value.
yeah. So the loss will be defined like this, right? So loss of W transpose X
And y.
and Y. So
I.
loss between this plus we use the regularizer.
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 So regularizer is a function of
W.
W. So I'll say that R of W, which is the regularizer. So regularizer can be lasso or reach. Uh, yeah, lasso means like norm of one, norm of L1 norm. In case of reach will be L2 norm. I think SVM we also thought that loss function in terms of
L2 norm.
regularizer, yeah, which is L2 norm. But yeah, this is general case. This is possible only, so whatever you have discussed till now is possible only in case of linear functions, right? uh, this is not actually a, if we are able to find out a solution in case of convex functions basically, right? Because all the linear functions are the convex functions, correct? If we think about any other convex function which will be a parabola and all, right? So parabola will be just like uh, non-linear function, but that also is a convex function, right? So we can actually set up this loss function, and we'll try to find out the solution to that by using the gradient descent method. But if in case you have non-linear functions other than that, and how we handle actually linear functions, sorry, non-linear functions in case of regression and all, regression cases, or maybe in SVM also.
Kernelize.
Kernel.
Kernelized, we take the kernel, we use the kernelized version, and we'll try to use it. But again, that will be the case, right? But there is another uh, good method or good algorithm which is called as a neural network, right? So neural network, this actually we don't have to uh, you know study this is in great detail, because deep learning will have all these things. But let us try to understand here again. So what is your perceptron algorithm? What do you do in perceptron? You have a data point x1 to, let's say, xd, right? Oh, sorry, maybe n,
Linearly
right?
separable data set.
Yeah, x will be rd. It is a linearly separable data set. And what do you do generally in classification task? You see the
W
sign of that,
transpose X. Yes, sir.
right? So let us say these, and each of x is in rd. So think of uh, okay, what is, how does this x vector will look like? Can I say
X1,
that it is
X2,
x1? Okay, let's say that x1. These are not the data points.
XD,
This is,
XD.
these are not data points, right? Don't confuse this with data points. This is what one data point which will have how many features? D features.
D
D.
features.
Fine. This is one data point with D features. And how does this W will look like? So W will be,
RD.
right, and the W will also be in RD, and
W1,
uh,
W2, WD.
to WD, right? Okay, and we take the product, and we then find out its sign. So consider this, all of these uh, features are like the single. Okay, this is called as a neuron. Okay, and let's say each of this is a feature. Fine. Let's say this is x1, x1 is x2, is x3, and up to xd. Okay, these are the features for one data point. And what you do generally, uh, you have w1, right, and you take the sum, right, w1, w2, w2, w3, and let's say wd, and you take a sum, and that sum will be what, w
W
transpose,
transpose X.
right. This was generally your perceptron algorithm or any other algorithm we generally see, maybe sigmoid also logistic function. In that case, what will happen here, you just use sigma here, and over that whatever the summation is there, and then you just get that sigma of w transpose x, right, and then you take a sign of it. Fine. This similar thing we can do with neural networks, but uh, what you do generally here, we have uh, three major type of uh, layers which we say. And what are those layers? These layers basically called as hyperparameters, but okay, that is a different discussion now. But let's say like first layer will be input layer. We try to do the same task but with the a different setup. Okay, input layer, another is called hidden layer. It can be one layer, or hidden layers can be one or more. Okay, yeah, hidden layers. And third one will be output layer. Okay, uh, so what will have this in the input layer? Input layer we will be having x1, x2 up to
XD.
wait, xd. Okay, so this is x1, x2, 3 to xd. And what we said is, uh, you will provide the input to uh, the output layer, right? Okay, so let us say you have some more neurons. What we say, when I draw any circle, it is called as a neuron. Okay, so what you do is you take all. So what are these?
W1,
W1,
W2,
W2, W3 up to WD, and what I'll get here,
W transpose X.
x, w transpose x. But as we said, right, if I have some sigma here, it will be sigma of w transpose x, right? So I'll take all that summation and I'll perform a sigmoid operation over there. This, so I can actually have different operations or different functions which we can use. These functions are called as the activation functions. Okay, so this is called as the activation function.
So sigma you are applying after calculating W transpose X,
Yes,
right?
yeah. First of all, so when this arrows will go, right, this arrows once it is so what, when it will reach to this point, it will always be a sum, right? And after that, we will so output will be sigmoid, that is called as activation function, and you calculate that sigmoid function over there. Fine. So let us say here is one activation function. Activation functions, there are different class of activation functions. Some of them are logistic function, ReLU, uh, rectified ReLU, different. All there are few more activation functions are there, and why we choose those only? Okay, there it's a very diverse discussion can be happened over there. But okay, so before going into that, what will be the output here? The activation of W transpose X, right? Fine.
Yes, sir.
So I am saying that this is neuron one. So
So
I'll
sigma
use
is one type of A function, right?
activation
Sigma is
function. Yes. Yeah.
okay, right, right.
Sigma is one of the activation functions. It can be ReLU, it can be rectified ReLU, it can be like different functions. So okay. Uh, Fine. Okay. I think ReLU is the rectified linear unit. There is a modified ReLU. Okay. There is another class of functions. Okay. That is not a primary discussion here. So here, if I use one, so activation functions can be sigmoid, can be, let's say, ReLU. There are like, so here in our syllabus it is having only sigmoid and ReLU. It can be anything. Okay, let us say this is one neuron. What we are doing here is we are actually taking all the summation over here, and then I am passing it through one neuron, and that will give me activated or maybe sigmoid of W transpose X in this case for simplification. We have one more neuron. What you do here for the second case, you give the input to this, right? This neuron also, and what will be the this will also have some
It will
weight
be a
vectors.
different W, right, sir? It not be the
Yeah,
same W.
yeah, it will be different W's, but it will be some weight vectors. Fine. So how to differentiate that? So let us say this is the first neuron, right? What I'm saying is this for the first neuron. Okay, first neuron. So these are the weights for the first neuron. Okay, and this for the
Second neuron.
second. And what is this 1, 2 to D will represent here?
They are the activation. Once you get the
These are the weights associated with the feature,
Second
that
yes, sir.
corresponding feature, right? So let's say W2 of 1. Like, let's say this W2 of 1. What does that mean? This,
second weight of first
yeah,
neuron.
second. So this weight corresponding to the second feature, right? And for the
First
first
neuron.
Neuron.
neuron in the hidden layer. So this is called as the input layer. This is the hidden layer. There is another layer we will discuss later on, that is called the output layer. I hope this is understandable. Fine. Uh, okay, and few more will be here. Okay, so I'll just draw with some other. I don't know how. Think this there. Done. Oh, not three. Maybe K. So you will have some K neurons in the hidden layer. Uh, that's okay. You will have activation functions here. So, and this is not necessary that the activation function for the first neuron and the second neuron will be same. It can be anything. Fine.
So activation for the first and second neuron can be different.
Different. That is possible. See,
Okay.
we are trying to what is happening here. You understand it. Let's say you have like simply for simplicity, we'll take two features. Okay, let's say x1 and x2, and let us say I'll take two neurons. Okay, maybe I'll take one more feature here, let's say, for understanding simplicity. So it is x3. Okay, this is my first neuron, this is my second neuron. What I'm trying to do here is this w1, this is w2. So let's say w21, sorry, w11, w21 and w31. Is that fine?
Yes, sir.
And I use sigmoid. So what will be the sigmoid of w1, or can I say that, let's say it will be uh, w.
W1 transpose.
Yes, so it will be w1 here, right? W1 transpose
Transpose XI.
x.
X, yes.
If I use x, then it's fine, or I can say wi transpose xi. Is that fine?
Yes, sir.
And here, what will happen? Here it will be another w. Okay, maybe I'll use color. This and this. So what is this? W1 of
Two.
2 is w1, sorry, w2 of 2, this w3
Three
of
of
2, and let whatever activation function I'll use, let's say, again if I can use actually again the same, but okay, that is not necessary. So w I 2
two.
transpose.
Transpose XI. XI.
So
If you
what is
use
happening?
I, then you have to sum over 1 to
Yeah, some, yeah,
3.
yeah, correct, correct. So
Sir, if this sigma one should be, is it possible to one have sigmoid and other have ReLU?
yes, yes, yeah, yeah, that is possible. You can do it. It's not like it is not restricted. What is happening here? Like that is the understandable part, right? So, what is happening? Let's say you have, uh, let's say in this case, let's say you had three features, okay, and let's say W3 of one, W3 of one is equal to 0. In that case, what is happening here? The contribution in the output from the third feature for the first neuron will be off, right? Right?
Yeah.
So it will just capture uh, things from x1 and x2. It will not capture the third feature.
Okay. Okay.
And let's say w2 of 2 is equal to 0. In that case, what will happen? The changes
X1
will
and
happen,
X3 only will contribute,
contribute
X2
to
will
the
not
second
contribute.
neuron.
Okay.
Okay.
Yes.
So these cases are very important where I think we have seen that eigenfaces example. If you remember, it's like long back PCA example, right? That was that there we had the images.
Yes.
Are you able to recall that? Like
Yes.
person's images will be there. So what are the important features? We said we use a PCA over there, but what are the important features we try to capture for an any human face? So can I say that eyes, ears, nose, possibly mouth, right, or hair, right? Let's say these are the five features which are uh, important to capture. Is that correct?
Yes,
Right?
sir.
So if I have five neurons in the hidden layer, okay, five neurons in the hidden layer, one, two, three, four, five. Suppose the first neuron is capturing only what, the
Yeah.
eyes or ear, right? One of the feature, and in that case, it will so the weights corresponding to other features will be might be zero. I'm not saying it should be zero or something like that, but this is the way it will actually work, right? Like mostly it will work. So what it does is it will just, so let's say this neuron has captured the feature ear, this captures, let's say, eyes, right? And third captures, let's say, nose, fourth captures hair. Fine. What we are going to do next, we'll be having one more neuron which is in the output layer. What it will do, okay.
It will linearly combine all the features.
So to combining all of this, what we need here,
Vector,
or weights,
W
right?
output.
Can I
Yes.
say that weights? Let us say it is W1 of the output. This is W2 output, and this is W3 output, and this is, let's,
WK, sir.
okay, WK, fine, WK output. And again, you might use the sigmoid function over there, or you just take whatever the final version is there. It depends on what problem you are trying to solve. If you are trying to solve the regression problem, do you need any activation function over here?
No, no, no.
No, right? Whatever the value is there, that will be a real value, and you can just keep it as it is. If you need the if the problem is a classification problem, what activation function will you use here? Probably
Sign.
sign off, right? So that is like up to you. But what is the final output here? W output
Oh,
transpose.
A into
Activation
A
of
activation of A W transpose.
Let us say W1, right? This was basically it was W1,
W summation of
WI.
W2.
you have to use
Yeah, that's
Summation I goes to 1 to K.
K
or
or WI transpose K, X and A of W two
okay.
transpose X like that WK.
I'll write down in mathematical format. So it will be y hat will be summation of I equal to 1 to
K.
k. K is what? Number of neurons in hidden layer,
Output
right?
layer.
Hidden rail.
Hidden there.
Is that fine? You just look at this picture. This is my hidden layer, right? And k comes from here, 1 to k, right? I hope this is clear. And we are combining all of that to get
W
the.
out I. W
So
out
can I
I.
say that w I
W out I.
I into
And A into
w
A of W
I
uh,
transpose x. Is
transpose.
that correct?
Yes. Yes, sir.
Right? It
Yes,
will
sir.
look like this. Okay, let's say w1 out activation of uh, w1, sorry, w1 transpose w1 transpose x plus w2 out uh, into a activation of w2 transpose x plus,
Yes, sir.
like that,
Like
up
that.
to w a out activation of w k
K.
transpose
Transpose.
x. That will be my output, and this is the output. If I wanted a uh, regression problem, I can just keep like this. If I have the classification problem, it will be sign of that, right? And based on the output,
If
because
you
it is good.
use different activations, then you have to write AI also, right? If you use different
Yeah. So
activation.
that is like you see, it's not, so whatever it is shown here, right? It is like simple problem, right? It's like, because we had one input layer, one hidden layer, and one
Output layer.
output layer. If you have more multiple hidden layers in between, then the that equation will become very large. Okay, but the final
So
thing is,
for one hidden layer, the activation function should be same, right? Or for different.
no. It can be different. That is like, there is no problem in that, right? Generally it
Okay.
is not like that. Generally it will be safe. But see, what is the harm, right? I wanted to capture only certain, okay, let's say that ear thing is there, right? I wanted a sigmoid to capture that. And for, let's say, nose and all, because it is shape, right? Generally it is like, it depends on not ear, eyes, nose, or like that. It will depend on the shapes, right? So how it is looking like. So if a shape or color or something like that, so we don't know, actually we don't know what is triggering it. But the thing is, uh, it can be anything. What I'm trying to say is, I can use the relu also. Relu is what? Max of 0 and z, right? It is kind of like that, right? You can just say that either 0 1 0 or 1, right? Kind of a Bernoulli thing. I'll just if it is active, if it is uh, less than this quantity, it will be considered as 0. If it is greater than this, it will be 1, or maybe some value. So it depends on how you wanted to capture the things. But it is not necessary that it will have the same activation functions, right? It can be different, or mostly it will be same. But that is not a case here. What is the next part? Okay, generally, but okay, that is fine. But how to define these weights? Okay, how many weights will be there? These weights are called as the parameters. So how many parameters we need to learn for this neural networks? Okay, all
K weights will be there.
said all 1 to w1 to wd.
That will be one weight, right?
So
Right.
let's say wk. Yeah.
The K is the number of neurons in the hidden layer, right?
Yes. Correct, na?
Yes. Right, right.
This was
And
right.
one weight will
The-
be for the outer layer because
yeah. So this
output
is, this w11. It will look like what? W
W1
uh,
to
one
W11 to W1D.
w1 to w1d, right? And that is what it is captured here. Fine.
Right.
And what is the next thing? What is w out,
Out
and which is in what is the dimension of w out?
K.
Right. I have this clear. But how to how to get these functions? So generally, okay, anyway, whatever parameters we have found out previously also in machine learning algorithms, how do you found out that?
Cross validated.
Or no, generally we do like we go from loss functions, right?
Yes,
try to
minimize
minimize
the
the
loss
loss,
function.
right? So what will the loss here? So if it is a regression problem, uh, this quantity over here,
As a
y hat,
sum
it is a,
squared
this
and
is a predicted label, right? So it will be, can I say that y hat minus yi? That will be my just general loss, right? If it is regression problem, it will be this loss. If it is any other problem, it will be accordingly. It will be changing, right? Uh, so how we solved it previously? We differentiated it and equated it to zero, right?
Yes, sir.
So here also we will have to do that, but that process is because it is not like one loss, right? You will have so here in this case, how many differentiation we should do? If you define some loss, it will be based on this W out and all the things, right? So how I'll get W one out, or if I wanted to go back and back, right? Generally, it
chain
is called as
rule.
we'll have to use a chain rule. You know the chain rule, right? All of you know the chain rule. So okay, I'll
Yes.
tell you. Let's say f of x, y, and z, right? If this is a function, then df, right, will be equal to del f by del x into by del y. Is that right? Uh, or okay, no, not this. Let's say if I wanted to say that I wanted to find df by dz, and here, okay, this will not be the case possibly. What we are saying is f is dependent on z, but uh, x is a function of, or y is a function of z, and also x is a function of y and z, right? In that case, it is possible, right?
Yes, sir.
All of you know this chain
Yes.
rule, right? Okay. Okay, maybe we will discuss it maybe the next part. But this chain rule, this method, right? This method is going to use there, and that is called the back propagation method. Uh, that is anyway, it's not there in the syllabus. What is about back propagation? We'll find out the loss at this part. We'll differentiate with respect to this now W out, right, and equate it to zero. We found out some uh, weight vectors there, and then we define the another loss here at these different points, and we again differentiate back, right? So in one go, how to differentiate it? So differentiate L with respect to out, then differentiate output, that like let's say this activation function with respect to these parameters, right? It's a complex thing. It's not that difficult, but yeah, that is possible, right? I hope that is okay.
Yes.
Uh, yeah,
Wouldn't this be like computationally heavy?
it's not actually, because generally differentiating, right? It's not that computationally heavy part generally, because we are actually not considering this part in terms of what do you say? We are at a time we are differentiating with respect to one parameter only, right? We are not, and we are
So,
able to keeping it constant. Huh?
so the loss will first differentiate with respect to W out,
Yeah,
and the result which we get will
again it will be
differentiate.
different. Generally, see, that is what we do, right? The back propagation is like you just this, let's say we differentiate this loss with respect to this, right? Suppose I'm just giving you the example. It might not be true, but yeah, let's say del w1 of 1, right? And like that, you just you will have to do different things, but it is not like the simple thing which I have written here. It will be little complex, but it is kind of like that. We just find out the loss here at this point. This loss is differentiated with respect to this, then this quantity will be differentiated with respect to this all the units, right? W1, W2, W3, like that. Fine or no? The other method is what? You can differentiate this with respect to output layer, right? Then
So,
you will be,
when we are differentiating, will the this A function be important? Because
yes, yes, because if it is sigmoid function, then you'll have to differentiate with respect to
Sigmoid
w, right?
function does not have a minimum, right? Sigma or yes, it will
It
have,
is, you
but
can find, right? It is 1 upon
yes,
1 plus e to the power
but it
minus
is
w.
not a convex function, right?
That is okay, that doesn't matter here. That is okay. So why this is useful is neural networks is because it is able to capture non-linear relationship. Mostly you see that image data, right? So any image data, any text transcription data, that can be very easily, or already it is there, like it is successfully uh, you know is done by using this neural networks, right? We can be able to process that data very successfully rather than doing the conventional machine learning algorithms. And why it is that? In conventional machine learning algorithms, right, the data which we need is a structured one, right? The tabular one where the numbers are there, like proper numbers are there, or the relationship among the features is also mostly linear. If it is non-linear, also it will be quadratic or some form. We can go into find into the kernel using the kernel. We go to higher dimension space and we try to find out uh, the relationship there. But this, for let's say, if it is a image classification, right, image classification task, where we able to do it very easily with respect by using, let's say, logistic regression or the svm. That is the idea here, right? So generally it will not perform better than the neural networks, because neural network, in this case, you can see, right, we will be able to use the different logistic functions and try to see whether which one is uh, good, right? So neural networks give the better results in case of unstructured
Non-linear,
kind of,
non-linear.
yeah, yeah, and
Okay.
non-linear relationship or unstructured data, which is images, or what, any text translation or the speech also, right? So these areas, this is very useful than the other machine learning algorithms. They will
Conventional
not,
kind of thing.
they will not be able to do it properly. For other data set, might be neural networks, like very structured one, right? Might be neural networks will not give the good results compared to them. Fine. So for example, if you have any regression data, when I say, is like you have good features with good numbers and good output label. In that case, it is possible that neural network will not perform better. It will
So for
perform.
structured data will use the conventional algorithm,
You can
and
use,
for
neural network also, but generally it will be at par of that, or maybe not better than the previous ones. The whatever you have, the unstructured ones, we use generally neural networks. Right? Unstructured data is kind of image files, or any
text or speech.
text or speech. And that's why it is actually, these are the very important and popular ones, right, nowadays. So whatever the AI methods currently are there, they are based on that neural network concepts only. Anyway, more things are also there, but yeah, that is the basis is the neural networks. And it is also, this idea also comes from where? Perceptron, right? Perceptron also, you can think of it as one kind of the neural network. Okay, this was there in week 12. You can go through lectures once more for better understanding. I think I've covered most of the things here. Shall we close it now then?
So neural, when we differentiate the neural network,
Hmm.
that function of the neural network, loss function of the neural network will not necessarily be a convex function, right?
Yeah, it is not required,
Okay. So
right?
if it is not convex, then we may not find a global minimum for that.
Yeah, so generally in neural networks, it is not possible that you always will find the global minima, but it will find you the local minima.
Local. Okay.
But that is fine. That, and because of that only, see, even if your function, right, let's say if your uh, data uh, is best represented by using, let's say, convex functions, right? In that case also, this neural network might not be able to reach to the global minima. and hence
So sir, here if we use the if we don't use the activation function, we
hmm,
simply use W transpose X.
then what is the
Then in
use of
that case, it
what is the
will
use of it?
be like
Then why we need a hidden layer, right?
okay.
Correct, na? There is no need, right? Then you can just directly,
But
because the
then
same thing,
it will be a convex function. It will be linear function only.
but we don't
If
need
a
that. That is what.
okay,
Correct, na? No, no. You are saying is right, because then it will be a combination of linear functions, and the combinations of anyway linear function is a convex function, and the combination of linear functions will always be a convex functions, right? Because sum
yes,
of all the linear functions will, or sum of all the convex functions is a convex function.
convex.
But the task of the neural network is not to work on the the convex functions. It is best suitable for the non-linear non-convex functions,
So
right?
typically, the loss function will not be a convex function.
Yeah, so
Mostly.
this is a very important understanding here is when you're uh, so you wanted to capture, if you wanted to capture a non-linear relationship, right? So the best suitable will be neural networks. If it is, if you wanted to capture a linear relationship, then uh, other methods are useful, right? So when to pick which one, which model, right? That is in your hands. Is that correct?
Yes.
So you don't need to necessarily use neural networks for like simple regression tasks. You can use a linear regression method using the ridge or maybe lasso also. You will get better results than neural networks. Fine, that is the understanding over here. Okay, yeah, I think that's it. So yeah, we will see, maybe we'll meet you maybe in the uh,
So here, the number of parameters that this neural network has
hmm.
is k plus one, right? K W's,
These are the parameters, no? So
k plus one parameter
why k plus 1?
because
K into
one is
D.
out also.
Okay, k plus
There
1,
are
but here, okay, one more parameter will be there. Actually, it is not written over here. It is a bias parameter. Each of the term will have, but it's okay. Yeah, you can say the k plus 1 because, okay, but that is dependent on what? How many number of hidden layers are there?
k is the number of neurons in the hidden layer.
Yeah, but here we are considering only single hidden layer. If you have multiple,
Okay.
then your parameters will increase. That's why
How
most of the very large, there are like very large neural networks will be there, like comprising of maybe hundreds of hidden layers. In that case, the parameters will be too high, right? So
okay.
that is one of the problem, as somebody has suggested, right? Like it will be computationally expensive at that time. But yeah, but this will actually perform better on the non-linear, to capture non-linear relationship with the unstructured data. Done.
Okay.
It
Okay,
will be
yeah.
K into D, no, sir, not K, because for each feature there will be a mapping.
So
So
here
X
you
of,
will have,
yeah, D into K, no, sir.
so if you actually wanted to see how many parameters are there, it's basically okay, yeah. So here in this it will have d parameters, right? D uh, parameters, yeah, or d weights here, and you have k. So k neurons, so it will be d into k. And again here in w output, it is not the single one, right? Again
K.
Plus
it will
K, yeah.
be 1 to k, so it will be k,
And
right?
then the
So
last one plus one, or no?
no, last one you don't need, so here we don't need, right? It's done.
Hmm.
We don't need the parameter there. W out is actually, w out is all this w1 out, w2 out to wk out, right now. So the total parameters, if I wanted to see here, with one input layer, one hidden layer, and one output layer, will be this d times k plus k. Hmm?
So this includes the individual elements of each weight, individual weights also. D into K plus K. Uh, we are not considering W11 to be a single parameter. We are considering its different components as different parameters.
For
Sorry,
each
can
feature, if there will be a different parameter for each neuron.
Sorry, I don't understand. Can you just repeat it once?
So what is this W11 and WK, W1 to WK? These are vectors, right? W1 is a vector containing
Yeah, yeah,
D
yeah, yeah,
components.
yeah.
So
It should
do
be
we consider W1 to be a single parameter, or we
no,
consider
no,
W1 to be a
all,
combination of
all
D parameters?
D parameters, because everything will have to learn, right?
Okay.
And
So
how we are going
W1
to
is
learn?
a combination of D parameters.
Yes, yes.
Okay.
Done. Okay, you guys can actually go through lectures. If any doubts will be there, we can take those into our revision sessions. Okay. Okay. Good night then. Thank you for joining it.
Thank you,
Sorry
sir.
for
Thank
the
you,
delay
sir.
today again.
Yes,
Thank
sir.
you, sir.
Hello.
Thank you, sir.